Electric fields. Okay, to start this video, I want to go back to talking about gravitational fields. And just remember the gravitational field strength of the Earth. We'd said that the gravitational field strength of the Earth, G, was equal to 9.8 newtons per kilogram. So that's for Earth. And then we also previously calculated that the gravitational field strength for the Moon was 1.6 newtons per kilogram. So I guess what I want to ask is, why are those numbers useful? What do those numbers tell you? If you think about it, what it tells you is, regardless of what force it's acting on, the force of gravity on the Earth is going to be greater than the force of gravity on the Moon. So in a sense, this G tells you how much gravitational force we have the potential to have. The potential for gravitational force. For gravitational force. Gravitational force. So if we had a 1 kilogram object on the Earth, it'd be 9.8 newtons. On the Moon, it'd be 1.6 newtons. It tells us that the Earth has more gravity than the Moon, and we don't really need to know what it's acting on. We're going to talk about a similar concept for electric fields. An electric field, sometimes it's written with the script E, or sometimes it's just written with the capital E. I just use the capital E. Is equal to KQ over R squared. This is a lot like little g, where it's GM1 over R squared. It's the constant, to make the equation work, one of the charges divided by the location squared. And this is just part of Coulomb's law equation, KQQ over R squared. But what we do is we say we don't care what this electrostatic force is acting on, but instead, if we didn't know that, how much potential for electrostatic force is there, or how strong is the electric field at that location? If I put a charge in it, how much force is that charge going to feel without knowing what that force is? So that's how we get our E right there. And then, just like we did with the force of gravity, if we know little g, then we get a nice little trick to come up with forces of gravity where we can take the little g times the remaining mass. Similarly here, if we come up with our electric field, then we can determine our electrostatic force much more easily by taking our electric field times our charge. So this says how much potential for electric force is there without knowing what charge that electric field would be working on to generate the actual force. With that in mind, there's a key difference between these two things. Specifically, typically when we're considering gravitational forces in any normal situation, we only have one object that's generating that gravitational field. But with charges, we can have many different charges that are working together to generate an electrostatic field. So our total electrostatic field can be found by finding the electrostatic field vector sum of the individual electrostatic field. So if I have more than one charge, like if I have a charge here and a charge here, and they're generating an electrostatic field here, then I can sum the electrostatic charges from the individual fields to come up with the overall electrostatic field here. The trick here, of course, is that this is a vector sum, so I need to consider their direction as well when doing this sum, and so it's a vector addition. Let's see what that looks like in an example. So again, we can calculate electric fields in electrical systems just like we do in gravitational systems. And one other key note that I forgot to mention here is that we are always assuming that the electric field is working on a positive test charge. So when we're considering our direction for electric field here at point B, what we should assume is that that unknown charge that's acting at point B is positive. And we'll talk about why that is when we go to use these electric fields later. So here's our example. Determine the electric field at point B in the diagram below. So we have charge 1 and charge 2 that are going to be working together to make that electrostatic field at part B. I can calculate the magnitude of those electrostatic fields by going kq over r squared at each individual location. And then I can come up with the total here, where I will also have to use the law of electrostatics when I'm considering direction. So let's just punch in these numbers here and get the actual values for these electric fields. So 9 times 10 to the 9, that's just the constant. The charge generating this field is 5 times 10 to the negative 6. Right, remembering that microcoulombs means negative 6. And here the distance between 1 and point B is 15 plus 20 centimeters, which is actually 35 centimeters. But of course we have to use standard units, 0.35 meters. Okay, so 9 exponent 9 times 5 exponent negative 6 divided by 0.35 squared. I got 3, 6, 7, 3, 4, 7. I'm carrying around a bunch of decimal places, whatever. This would be in newtons per coulomb, since I'm missing one of the charges here, so it's per coulomb. So that's the electrostatic charge from that one. And here, 9 times 10 to the 9. Again, because I'm going to use the law of electrostatics to determine my direction, I'm not going to bother with my charge right now, so I'm just going to put this in as 2.5 times 10 to the negative 6. I'm ignoring this negative because I'll deal with direction later. And here I'm 20 centimeters, or 0.2 meters away. So 0.2 meters squared, 9 exponent 9, 2.5 exponent negative 6 divided by 0.2 squared. And I got 562,500 newtons per coulomb. I'm going to put commas in so that I can see my numbers a little bit more easily. Now, to consider my directions on these two electric fields, remember I'm at point B and I'm positive. I'm using a positive test charge here. So I'm going to look back at my individual charges and I'm going to see if I'm attracted to them or if I'm repelled from them. So considering this charge, which is what I did down here, this charge is positive and I'm positive. So like charges repel. So this charge will make me want to run away. And I'm going to call that my positive x direction. Alternatively, this charge is negative and I'm positive. So unlike charges attract, which means this charge 2 will cause me to be attracted in towards it at 2. So that's going to make me negative x. Or I can just handle that by making the whole number negative 562,500 newtons per coulomb negative, and then that's in the same positive direction as that. So basically this one's going right, that one's going left, and the way that I'm going to handle the left is by making it negative. Now with those two electric fields, if I want to know my total electric field, I can simply add them, but as a vector addition where I consider their direction. So ET equals E1 plus E2. E1 is 367,347 newtons per coulomb in the positive x direction. E2 is negative 562,500 newtons per coulomb. It is in the negative x direction. That's what I've represented here. So when I add those two things, or really subtract them because they're going in opposite directions, I get negative 195,153 newtons per coulomb x, or let's say 1.95 times 10 to the 5 newtons per coulomb in the negative x direction. So what does that mean? Well, that's how much force could exist at that point if I put a charged particle there. I don't know the exact value of the force because that would depend on the actual charge that I placed at that location. So if I wanted the force, F equals EQ, I'd have to know that Q. But in the meantime, I know the potential for the force. I know how much force could exist there, how strong the electric field is, without knowing what charge that it's acting on.